we want to take Newton's second law into the vertical direction, which means we have to deal with an extra force that doesn't usually come into play in the horizontal direction. We have to deal with weight. Okay? And I'm guessing you guys have a pretty good idea of what weight is and where it comes from, but we want to be explicit about it. Okay? So we're going to start with Newton's second law. And remember, Newton's second law says net force equals mass times acceleration. Okay? That little sigma symbol means add up all the forces acting on the object, and then we can tell some stuff about it. Now we're going to start simple. Okay? An object in free fall. Do you remember what that means?
It means it's just falling with no other forces acting on it except gravity.
Right. So the only thing pulling down on it is the force due to gravity. There is no air resistance or anything else to worry about. Now, when you guys draw a free body diagram, just a refresher, right? These are important. Forces start on the object. Okay, the arrow points in the direction of the force, and the force gets labeled with what causes it. That's called the agent. The agent for this one is gravity. Okay. Now, the force due to gravity has its own special name. Okay, because it is so prevalent and it does affect a whole bunch of things. We call it weight. Okay. Well, if we use Newton's second law and try to figure out what's going on here, what's this block or object doing?
Well, if it's in free fall, it is accelerating. And
Right.
we learned before that the acceleration due to gravity is 9.8 meters per second per second.
Right. And is there anything about this free body diagram that lets us know it must be accelerating?
Oh, well, the forces on it are unbalanced. Because
Right.
we've only got one force on it, there's nothing else to
Right.
cancel it out and
So we
balance
just
it.
have one force. So our net force, we don't have to add anything together. It
It's
is
just Fg.
Fg.
There's only one.
And you said that you know what the acceleration is.
We also might know the mass.
It's
Yeah.
g, right? We know that the acceleration is g, 9.8 meters per second on Earth, right? Now this is not a universal constant, okay? This is just Earth's the acceleration in Earth's gravitational field.
Right. If we went to a smaller planet, it'd be smaller. If it was bigger, it'd be bigger.
Okay.
But we're going to stick on Earth.
We're going to
mostly.
stick on Earth mostly, and for now we're on Earth. All right. So what we have is net force is Fg. It equals mg instead of ma because the acceleration is the acceleration due to gravity. And that gives us this little equation that tells us that weight, Fg, the force due to gravity, is just mg. Okay. Now, this is a force. It's not mass, but it does depend on mass. Okay?
Sure, because if I add mass, I weigh more, right?
Right. And we're physics teachers and we make the distinction between mass and weight, but sometimes it's used interchangeably. And we really shouldn't do that. On Earth it's okay because we understand that 1 kilogram has a weight of 9.8 newtons, and so we can go back and forth. But weight changes depending on where you're at on the Earth, how far you are from the Earth. Mass doesn't, okay? And
yeah, mass is inertia. Or mass measures inertia.
Mass measures inertia, okay? So
and weight is a force. And
so right, mass
inertia
is telling
and
me,
force aren't the same.
right. Mass is telling me how much matter's actually in something. Weight is telling me how much force is acting on it because of gravity. And so because of that, remember, we're going to have different units. Mass is measured in kilograms, and weight is measured in newtons. Okay, and in the English system, it's measured in pounds. Okay, so just keep that in mind. Now, this was a simple case. This was free fall, only one force acting on an object. Okay? What happens if it's not in free fall? What if it's sitting on a surface?
So then we're going to have the normal force, right?
Right.
So then is normal force going to be equal to weight?
Well, it can be, okay, but not always. Okay, the normal force is not weight. And if we really think about what the normal force is, okay, I'm going to draw a little picture over here. Okay. Here is an object, and it's got some mass. It's hanging out here. What forces act on it if it's sitting on this table?
And it's at rest?
It's at rest.
Okay, so I've got Fg going down.
Okay, so the force due to gravity pulls down on it.
And I've got the normal force acting perpendicular to the surface.
Acting perpendicular to the surface. So I'm going to go ahead. This is the normal force, the force from the surface. Now, why does that force exist?
It's because the table is exerting the force on the box. It's kind of a Newton's third law thing, right? Like,
right. Because the box is being pulled into the table. The table is pushing back up on that object. Okay. So it is a reaction force. It's actually trying to balance this force, right? As hard as this thing's pushing down, it's going to get pushed back up. Okay. And so I have this, I say it's reaction force, but that means the normal force is only going to be pushing up with enough force to keep things balanced a lot of times. Okay, so if we have Newton's second law, net force equals mass times acceleration, and I wanted to break that out explicitly here, what would I say?
Okay, so that little sigma means sum of the forces, right?
Right.
So I've got two forces acting on this box. I've got the normal force up and the gravitational force
Right.
down.
So two directions, we need a positive.
Okay, so we're going to say up is positive. So I've got the normal force plus, or you can say minus,
right,
whichever.
because it's plus a negative
gravity.
Fg.
Yep.
This equals, and in this case it's at rest, so and it's remaining at rest.
So it equals mass times acceleration.
But that
is also going to be 0 because if it's at rest, it's not
right.
moving.
So for this particular instance, the normal force actually minus Fg equals 0.
So we can rearrange that. The normal force is gravity.
The normal force is the force due to gravity. It is weight in this case, but it doesn't have to be that way. Okay, so if we have a beam that is attached to a couple cables, and these cables are attached to a crane, okay, and so the crane is lifting my beam. Okay, now let's start at the very beginning, before the crane really starts picking it up at all. So we're going to say that the tension here is, well, it starts at 0 and it's going to go up. So we're at the 0 point. What other forces are here?
So
and
again,
this beam is sitting on.
It's on the ground. Okay,
the ground.
so we've got still gravity and normal force, just like our previous example.
Still gravity and still the normal force, just like our previous example. Okay, but now when I go to write the Newton's second law equation, okay, I'm going to want to include this. Okay, so there's going to be some tension here eventually, and it's going to be up, right, because the crane is lifting it up. So again, up is my positive direction. So if I look at the net force,
okay, so now we've got three forces acting on it. We've got tension, and it's going to be positive.
It's going to be positive.
We've got the normal force, positive also, because it's pointing up.
As well.
And gravity going down.
So negative.
So negative for that one.
And this equals.
And is it at rest?
It is at rest.
Okay, so
I'm just going to go with 0.
That's going to be equal to 0.
Now, let's say the crane starts to actually exert some force and start to increase the tension in the cable. Does the beam come off the ground right away?
No, it's going to have to overcome some force first.
Right.
It won't come up right away.
This normal force is exerted by the ground because when it's sitting on the ground, what's supporting the beam? The ground, right?
The ground.
Okay, all right. Well, all right, so if this is 0,
okay,
then the normal force and gravity exactly balance. But let's say this isn't 0. Let's say it gets just a little bit bigger. This is getting bigger and bigger.
Bigger, then to counter that, if it's still at rest, the normal force must be getting smaller, right?
Right, because the tension plus the normal force, if we just rearrange this equation, has to equal
Fg.
Fg, okay? And gravity's not changing. So if this force is getting bigger, and this force is remaining the same,
so
the normal force
must be getting smaller.
And eventually, tension increases, tension increases, tension increases. Eventually, the beam comes off the ground, and at that point, the normal force will be...
It'll be gone.
Gone,
so then at that point, will the tension be equal to Fg?
Then the tension will be equal to Fg, unless, of course, it starts accelerating up, and then this isn't 0. And so then if this beam accelerates up,
then Ft must be greater. If it's going up, then that one needs to be greater.
Well, if it's accelerating up, right?
Yeah,
it could be moving, when the forces are balanced, there's two possible states, right? Moving at a constant velocity or not moving.
But to get it moving up, the Ft is going to have to overcome the gravity.
Bit, right? To accelerate it, it did have that instant where it was accelerating.
But then once it moves at a constant rate, then they'll be the same again. So it's actually a lot of things going on.
There is a lot of things going on there. Now, you could do the same problem in reverse, right? So instead of a crane lifting it up, you could have a person who steps up onto the beam. All of a sudden, if there's no tension in this cable, but there's an extra person over here, okay, well, he's standing on it, so gravity's pulling on him. Okay, so there's this extra force down, so that means the normal force will go up. And so it's not going to be equal to the beam's weight, it's going to be equal to the beam's weight plus the guy's weight. Okay.
So this really shows you that it's very important to draw a free body diagram for these pictures, for these situations.
It's not hard to do, you just have to keep track of all your forces, right? And we'll see later that when we start getting into 2 dimensions, the normal force can really do some funny stuff. Okay, but for now, just be sure that you keep track of the normal force and which direction it's in, and all the other forces as well. Draw your free body diagrams, do it right.